Here's a second type of ice table you might encounter in your study of equilibrium. So let's get started on this one. Again, just a reminder, in these ice table calculations, sometimes you might have to end up solving the quadratic equation. All right, the negative b plus or minus the square root of b squared minus 4ac all over 2a. Remember that from high school? That's the quadratic formula. So if you don't remember how to do that, download the file from D2L called Algebra Review and make sure that you are familiar with how to solve the quadratic equation. Because there are some times when we're doing ice tables where you're going to have to end up solving the quadratic equation. It's just sometimes it can't be avoided. So please make sure you download that and refresh your memory on the quadratic equation. So here's a problem. And I've given you the value of k. But I haven't given you any information about concentrations. So that's completely, we don't know how much is in there at equilibrium. All we know is how much we're starting out with. So the problem says that I have 1 mole of each reactant in each product, and I put them into a 1.5 liter flask. So I know how much initially I have, but I have no clue how much is there at equilibrium. So we're going to have to use an ice table to figure out how much is there at equilibrium, and then go from there. So the first thing you need to do, get in the habit of doing this because you'll save yourself a big headache. Always, 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 if your concentrations aren't given to you in molarity, go ahead and convert them to molarity. Okay? Because remember, when we're doing ice table calculations, we're dealing with concentrations. We're not dealing with number of grams, we're not dealing with number of moles. So if the information you're given is not already in moles per liter, take an extra second and convert everything to moles per liter before you plug into your ice table. It'll make your life a lot easier. Okay, so the problem said that I had 1 mole of each substance. So moles divided by volume gives me molarity. Moles divided by volume, moles divided by volume, moles divided by volume. And you can just carry out extra decimal places here. Now notice they're all the same, right? Because you have 1 mole of each of them. And 1 divided by 1.5. It's going to be the same for all 4 substances. So you can carry out as many decimal places as you'd like right here. We're going to be, doing our arithmetic with rounding at the end. Okay, so all of my initial concentrations are the same. Now, we know based on the law of conservation of mass that as this reaction proceeds, carbon monoxide and water concentrations are going to go down, right? Because for this reaction to go this way, these 2 substances concentrations need to go down. So these are going to go down. And likewise, these concentrations are going to go up. But we don't know how much they're going to go down by or how much they're going to go up by. We just know that they're going to go down. Right? So the amount that the reactants go down by is the same amount that the products go up by. Does this make sense? Make sure you understand why we're doing this. Okay? We know that these concentrations are going to go down. We don't know how much they're going to go down, but because they are reactants, their concentrations are going to go down. And the amount that these go down by is going to be the amount that these go up by. Okay, so all we're doing is solving for x. And then once we know the value of x, we can subtract it if it's a reactant, and we can add it if it's a product to get our equilibrium value. So here's what my table looks like right now. 0.667 minus x, 0.667 minus x, 0.667 plus x, and 0.667 plus x. So now all I need to do is figure out how to solve for x, and then life will be good. So the way we do that is we're going to use the value of k. Right? The problem tells me that the equilibrium constant is 5.10. So if I write an equilibrium expression and set that equal to 5.1, then I can do some arithmetic and solve for x, which I can then plug into my table here to get equilibrium concentrations. So there's my equilibrium expression. So 0.667 plus x for that, 0.667 plus x for that, 0.667 minus x for that, 0.667 minus x for that. Now this times this is the same thing as 0.667 plus x, quantity squared, right? And this is the same thing as this from an arithmetic standpoint. So now I can really simplify my math because the top is being squared and the bottom is being squared. They're both being squared. You can only do this if both the top and the bottom are being squared. If one of them was being squared and the other one wasn't, you can't do this. But because both the top quantity and the bottom quantity are being squared, I can just take the square root of both sides and it simplifies my math. Again, you can only do this though if both the numerator and the denominator are both being squared. So I take the square root of both sides. Square root of 5.1 is 2.26. So 2.26 is equal to 0.667 plus x over 0.667 minus x. So now all I need to do is rearrange this and solve for x. So multiply both sides by 0.667 minus x. And that's what gives me. And now collect like terms, right? So if I subtract this one and put it over here, and subtract this one and put it over here, here's what I'm left with. All right, so we're just doing a little bit of cleaning up on our math. And now we've got this expression. To get x by itself, we're going to divide both sides by 3.26. So x comes out being 0.2578. But we're not done yet, right? All we know is the value of x. We're only finished once we plug x back into our ice table. So when I plug x back into my ice table, these are my final equilibrium concentrations. We subtracted it from the reactant side, we added it to the product side. And since all of these are already molarities, I don't need to worry about converting it because everything is already in moles per liter. And we're done.